Now we will examine various counter circuits used in digital equipment. Because of their versatility, counters are used in many applications, such as arithmetic circuits, code converters, analog to digital converters, and waveform generators. This part of the video will concentrate on basic counter circuits. The primary function of all counter divider circuits is performed by the flip-flop, which, as you have seen, changes state when the clock pulse does a positive or negative going transition. We will begin our study of counter circuits with the basic ripple counter like the one being shown to you now. When a square wave signal is supplied to input A of the first flip-flop, it will produce a high at its output Q1. This high at output Q1 is then fed into the input of the second flip-flop. The output at Q1 is also used to drive other digital circuits, which will be discussed later. Notice that the duration of Q1's output lasts for one complete on-off sequence of the clock pulse at input A. Since the input of the second flip-flop stage is controlled by the output of the first stage, it will also go to a high state. Notice that the output of flip-flop 2 will remain high for one complete on-off sequence of flip-flop 1. Also notice the duration of the output on flip-flop 2 is 2 complete clock pulses. Next, the high output of flip-flop 3 is fed into the input of flip-flop 4. As you can see on the waveform, the output of flip-flop 3 will remain on for one complete on-off sequence of flip-flop 2. Therefore, the output at Q4 will remain on for 4 complete clock pulses. And finally, since flip-flop 4 is controlled by flip-flop 3, it will also produce a high output. The duration of this high output will be for one complete on-off sequence of flip-flop 3. Therefore, flip-flop 4 will stay on for 8 complete clock pulses. Since the flip-flop only has 2 states of energy, either on or off, it produces a binary count. The first flip-flop stores up to 2 counts, the second stage stores up to 4 counts, the third stage up to 8 counts, and the fourth stage up to 16 counts. Since this counter starts at 0 and counts up to 15, it is called a binary up counter. The simple ripple counter just described is called an asynchronous counter because one stage triggers the next. There are, however, disadvantages to this type of counter. One, the ripple counter has a much slower operation than do individual flip-flops. And two, the inability of the outputs to switch at precisely the same instant due to the propagation delay of each flip-flop stage. All logic devices will contain some propagation delay, and this becomes a problem when the stages are wired in series because the delay times are cumulative, in that the delay time of each stage in the series design will add to the total circuit delay. This problem is overcome by the use of synchronous or parallel counters. When wired in the synchronous configuration, all flip-flops are triggered at the same instant. Here we see a logic diagram of a synchronous counter. These counters are available in a wide variety of sizes and with a number of standard output decoders. As you can see, each flip-flop is controlled by the clock signal. Whatever data is entered must be entered with each clock pulse, because only when the clock enables each flip-flop can the counting or dividing operation take place. Notice that all the outputs, Q1, Q2, Q3, and Q4, have the same symmetrical pulse shape. Each output pulse will be the width of one complete square wave cycle of the clock pulse input. Also note that each output occurs one complete clock cycle after the previous one. The reset signal can be enabled at any time and is generally kept at logic 0 after the start. Also, as long as the clock inhibit signal is at 0, the counter will advance one count during each positive clock pulse transition. Since the synchronous counter does not have nearly the propagation delay of an asynchronous counter, it is better suited for high-speed operation. However, some delay does still exist, and the actual operating speed is somewhat less than the maximum theoretical speed. This is due to the fact that since the clock must drive all the flip-flops simultaneously, it requires more power from the clock circuit. When the clock is heavily loaded with flip-flops, the propagation delay is increased and the counter speed is reduced. Despite this limitation, the synchronous counter circuits are still superior to the asynchronous counter. Oftentimes, counter circuits are designed to perform a specific task. One such application would be in the division of a given clock signal by a pre-selected value. This function is easily performed by a programmable counter. Programmable counters are used in frequency synthesizers, phase lock loops, and other applications which require frequency division. A variety of programmable counters are available on today's market. By presetting the stages of a counter, you can design a circuit that in some cases will count either up or down, because each separate stage can be made to reset when the preset count has been reached. Here we see a typical programmable divide by n counter. Notice the inputs labeled P1, P2, P3, and P4. These are the counter inputs which can be programmed to allow the user to determine the desired division of the input clock frequency. Also notice the input labeled PE. This is the programmable enable input. This allows the counter to divide by the pre-selected value at the inputs of P1 through P4. Next is the input terminal, labeled CF for carry forward. This input is used for cascading the counter when a higher value is needed than that which can be achieved from a single stage. The terminal labeled 0 is also used when cascading stages together. CF is the input and 0 is the output. The clock inhibit input allows the pulse counting function to be disabled. The reset, clock, and outputs Q1 through Q4 perform similar functions as have already been described in the previous counter circuits. Now that you know what the input and output functions are, let's examine this circuit to see how it works. We will start by programming inputs P1 through P4 with the binary number 9. P1 will have a binary weight of 1, P2's binary weight is 2, P3's binary weight is 4, and P4's binary weight is 8. So the input signal placed on the P1 through P4 will be 1, 0, 0, 1 respectively. When the programmable enable input is momentarily taken high, the internal preset logic is enabled. This allows the number appearing on inputs P1 through P4 to be loaded into the counter and appear at outputs Q1 through Q4, once the desired number has been preset. The counter will begin counting down from the preset number. It will do this on the first positive transition of the clock signal. The counter will continue to count down on every positive transition of the clock signal. For the first 9 pulses, output 0 will remain low because the count has not yet reached 0. On the 10th transition, the counter goes to 0, 0, 0, 0 at outputs Q1 through Q4, and output 0 will go high. As you can see from the illustration, the clock pulse was divided by 10. For every 10 clock pulses, output 0 would go high once. Now let's see how a programmable counter would work in a typical application. Here we see a simple block diagram of a digital clock. The first block in this system is a 40 kilohertz oscillator. It will produce a series of 25 microsecond pulses into the first programmable counter. As you notice, the first counter is a divide by 40,000 counter. In other words, for every 40,000 clock pulses, this circuit will produce 1 output pulse. These pulses will occur at a rate of 1 each second. The 1-second pulses are then fed into a divide by 60 programmable counter. This counter has 2 outputs, one of which is used to drive a binary to 7 segment decoder driver circuit, which further drives a 7-segment display. This part of the system is used to show the seconds on the clock. The other input is fed into another divide by 60 programmable counter circuit. This circuit also feeds a binary to 7 segment decoder driver circuit and 7-segment display. This part of the circuit is used to show the minutes on the clock. The second output from the divide by 60 counter is fed into a divide by 12 counter, which is used to show the hours. An actual clock circuit of this nature would be a little more complex than the one being illustrated, but the operating principle will remain the same. So far, you have seen how flip-flops may be connected to count from 0 to the modulus number, or from the modulus number to 0. The modulus is an integer which designates the number of states through which a counter sequences during each cycle. But what happens if there are two numbers to be combined within the system? After all, this is what the computer does best. This simple combining of numbers is performed by circuits referred to as